Okay, I'll start again. So basically, my study is on the shape optimization of the R37 compressor blade using a gradient-free optimization toolkit or surrogate-based optimization. So it's just a short primer on SU2 and its relationship with Cenaero's relationship with SU2. Um, for this project, we are concentrating the CFD solver SU2. Normally in Cenaero, we use ELSA for design optimization of turbo machinery blades, both the turbines and compressors. But recently, for the past 2 years, we have dedicated a lot of effort in using SU2, and a great deal of effort has been put into plugging SU2 into our design optimization chain. Cenaero is part of the Turbo Machinery Working Group, which is led by Tu Delph and Matteo. And we actively participate in this group every month. It'll resume in the following weeks. So, blade shape design is an integral part of compressor performance. And here's a list of references, recent references, where there are various different methods of blade shape design. And currently, what we're using is freeform deformation tools that is developed in Cenaero, primarily for autogrid. And for example, here are recent examples of uh, blade design used in the current engines. They also used in wind turbines and also in small consumer electronic goods. For our case, for the R37, it's an aeromechanical optimization, and it's on three regimes. Uh, the nominal one, which is 100 NN, the 90 NN is slightly lower speed, and 105 NN is slightly increased from the nominal, with 90 parameters and total of 5 operating points. So this is like the perspective on the R37 compressor blade. The R37 compressor blade was introduced around the 70s, and there's a paper that you can reference that gives you the detail of the blade. It's actually a highly loaded supersonic compressor blade, which has a lot of shock, uh, boundary layer separation, and large tip vortices. So it's ideal for benchmarking new solvers and current solvers. And a lot of the open source I mean, non-proprietary shape optimization studies use the R37. For the current study in SU2, we're using the row with muscle steam for the convective steam, and I'm using the K omega SST model for the turbulence. The inlet conditions are set with interpolated from a file, the total conditions, and our outlet is basically static pressure with radial equilibrium using the Gill's functionality. This dark region is the rotating part, whereas the upstream and the downstream, the light regions, are fixed, the non-rotating parts. This is a schematic of the R37 blade, and in our case, we're not using the bleed. There are cavities for the bleed, and one can use them, but in our case, we're not using them right now. The meshing is primarily done with the Cadence Autogrid mesher. It's a multi-block structured mesher with and the blade has a periodicity of 36, and we're just using one row with periodic boundaries, and it has 3.5 million grid points. So this is the Cenaero FFD box. So basically, in our case, we're not deforming the mesh. We're remeshing at every step. Every time there's a new experimental candidate from the optimizer or the DOE, we remesh. And this FFD box was primarily created to interface with the Geom Turbo from Autogrid. And here's an example of deformation where the light green is the newly optimized blade and the dark brown is the reference blade. So we have a total of 45 parameters for X and 45 parameters for Y, with the relative uh, displacement of minus 0.25 and 0.25 in the X and Y parameters. So total we have 90 parameters. So this graph shows the experimental data of R37. So this study was done last year in validating SU2 with the R37 experimental data. And this bottom dashed line with the circles is the current SU2 control point. The points at different outlet static pressure. So the yellow one is what we're trying to optimize, and we're trying to raise it. Well, the other blue ones here and here are constraints. So that the idea is that if I just optimize this point and don't include these in the design space, then if I try to build an ISO line for the optimum experiment or candidate experiment, there could be cases where the SU2 solver, there could be divergence, or this solver fails. So my ISO line would be incomplete. So putting these inside my design space helps the optimizer determine what, if in case there's a failure, not to go there. And for the lower speed one, we have a point over here, which is a constraint, which is midway into stall. So in all, we have 5 control points and 3 regimes. And one of the major constraints afterwards is for the higher speed case, which is 105 Nn, where we use the von Mises constraint. And in our case, for the SU2, we are only using centrifugal forces. We're not doing the pressure mapping yet. That's something we need to do. So this is the complete design chain for our Minamo optimization platform, which is currently we're using version 4. So basically, you have a DOE of design of experiments, and then from the design of experiments, you start the optimizer, and it automatically it basically checks for successes and failures, and then based on that, it enriches the zones where the experiments are more feasible. And so these are the various steps. So we start with the FFD, we go to the autogrid, then we go to SU2, then the SAMSUF mechanical solver, and then we post-process the result. So as for the results, so I'll start a little slowly here. First of all, so we started off with just 100 design experiments, which is coarse, but I also wanted to test the latest version of Minamo, how it could handle a coarse DOE. There are around 50. So this is the original DOE for the 100 NN case, and this is the black line is your reference R37 performance of the reference, and you can see it's coarse, and they're around for 50% failures, which is pretty high. But anyway, Minamo is able to enrich the design space, and with just the aerodynamics, the aerodynamics optimization is able to push the isentropic efficiency to above 88%. So what I did gradually was I gradually increased the constraint on the efficiency, and I kept the constraint on the pressure ratios stable, and I kept increasing it, and the optimizer was able to push the optimum above 88%. But this is just for the 100 NN case. It has to satisfy the other 2 regimes and the other 3 control points also. Now, for the mechanical case, what I did was that I collated all these experiments and created a new design of experiments, filling them in, simulating the mechanical part, and then relaunching the optimization. And for the optimizer with the arrow and the mechanical part, it starts to drop because of the addition of the mechanical constraints. So this is for the lower speed one. In the lower speed one, somewhat the converse happens. When you just have the aerodynamics, what happens is that the increase is very gradual. But then when you add the mechanical constraints to the optimization, it starts to go up. more than the constraint that I applied. And the constraint that this orange line, I have increased the constraint from the baseline. So I'm trying to push the optimizer to keep improving the performance of the blade. As you can see, when you just have aerodynamics and then you solve for the mechanical part, almost all the experiments violate the mechanical constraints on the suction side and the pressure side. And it's only when you include the mechanical constraints and run the optimizer that they slowly stop violating the constraint. And so this is where we at over here, where the optimum is, well, the candidate optimum. So here is the global performance. So the efficiency is over here. The blue line is basically the reference R37, and the yellow line is our candidate experiment, where you can see there is a marginal increase in the 100 NN case and a slight increase in the 90 NN, where the 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 objective function, which was SQ3, has increased by relatively 2.7%, whereas there's certain other points that have increased about 3%. The performance for the lower speed one is more constrained. It's less ambitious, but that's acceptable right now. Here are the radial profiles at the exit for the isentropic efficiency and the total pressure ratio. These are for separate operating conditions like SQ3, SQ12, and SQ1. And you can see that there is an increase in efficiency of the radial profile. For the total pressure ratio, there is an increase midway, but then near towards the tip, the optimized blade, which is the solid line, there is a slight drop in the total pressure ratio. Uh, this I'm trying to figure out why exactly it is. It could be due to the losses due to the vortices and the shock tip leakage interaction, but it's an ongoing thing because I don't my unlike ELSA, my SU2 post pro tools are not complete. This is the so what we do is that we plot the isentropic Mach number at different stages of the blade. And isentropic Mach number is a constraint. From 20% to 80% of the blade, I want the isentropic Mach number to be below the reference blade and the max isentropic Mach number. So in some cases, towards the hub, below 50%, the blue line, which is the optimum, it's more loaded. It has a higher isentropic Mach number, but towards the tip, there's a slight reduction. So it starts to unload towards the tip. For the 90 NN, you can see the variation again, where in some cases, in some regions, it is lower. The max isentropic Mach number, the shock is less stronger than the reference. This is a static pressure contour on the blade, and not that, I mean, it's quite subtle, but you can see, like, for example, here the shock jump is for the reference is a little higher than in the case of the optimum blade. It's more darker blue here with a slightly lighter blue here. And same cases with the other cases, but it's not, I mean, it's somewhat subtle. It takes, I mean, it's a little harder to see on the screen like this. This is the pressure contours on the shroud, and you can see that there's a distinct change in the way the shock tip leakage vortex interacts, where there are more losses with the highest blue region of the static pressure for the reference cases than in the optimum cases. Like you have higher losses over here, and this is more local. In some cases, it's not that discernible. They're very close. Like for example, over here for the higher 105 NN at SQ8. So in terms of conclusions, well, one of our goals was to get surrogate base, I mean the SU2 into our design chain, into our design platform, and we've been able to do that. And there has been some marginal improvement in the ISO speed lines in terms of the performance of the new blade. For the current study, I did not include sweep and lean, but I should include sweep and lean for the next study, where I include the pressure mapping of the structural forces on the blade. When we include the mechanical constraints, oh, it's running out of battery. When we include the mechanical constraints, we do notice. Yeah. Okay. When we include the mechanical constraints, we do see that the efficiency performance drops for the nominal case, but for the 90 nm cases, it starts to increase. For future work and perspectives, right now we're not able to get multigrid to work with periodic boundaries. It's something that we would like to look at in the turbo group. And there's another situation where if you cannot restart from a new geometry. I mean, you cannot. What happens is that if you have a new geometry and you want to restart from from the solution from your reference geometry, you cannot do that. It basically the final result is the reference geometry. Then the other one is the valve mass flow with reference static pressure to drive the flow. That's pretty much industry standard, and we need that because right now what I'm using is the static pressure, which is not exactly the norm. And the next big thing we would like to do is implement multi-point optimization with the discrete adjoint method in SU2 on the R37 compressor blade. And then also I need to complete the post-road tool for SU2 turbo machinery. Right now we have a lot of tools for ELSA, but in order to fully analyze the flow in detail for SU2, we need to increase a repository of tool. Lastly, in terms of acknowledgement, I'd like to acknowledge the Wallonia region for their contribution, especially the having access to Lucia, our HPC system. I would like to acknowledge the SU2 Foundation and also the Turbo Machinery Group led by Matteo for their advice, help, and I would also like to thank my colleagues at Cenaero. That's about it right now.
All right, thank you, Ashvin, for this nice presentation. We have room for only one small question, maybe. You have something?
So I would like to learn a little bit more about the restart model, and I understand because you're rematching the grid topology changes, so you don't have matching nodes between the two meshes, and that's why you cannot restart from the solution.
Well, actually, it works for external flow problems. It doesn't work for us in turbo machinery. That's what I noticed. Like when, for example, at first when I ran the R37, the let's say the reference case, and then I remeshed for let's say a new geometry, and I restarted from the existing solution, I found that it basically the solution was that of the reference case and not of the new geometry. And apparently and then when I interacted with my colleague who was doing the same thing for an external flow problem, they didn't have that because SU2 was actually interpolating the information. In our case, it wasn't, and I think it's something to do with the periodic boundaries or something. So for me, what I would do for each case was run a first order solution, and then do the second order.
So that's all later than that. It is
But it's an issue. But every future, the endpoints, not endpoints are teaching the two meshes. If the endpoints are teaching the two meshes, yeah, because if the imposition is to endpoint identification. All right. Yes. Good. Okay, thanks again, Ashvin.
Yeah.
This is-